Hi, everybody. This is a great honor. And hello, everyone out there in Zoom land. I saw some familiar names up there, so it's great to see you guys, so to speak. And my wife is in on Zoom. That's a first. That has never happened before. Hi, Allie. You're awesome. The thanks. So what I'm going to talk to you about today is a body of work we've been doing for a while, and it's published in a series of 6 papers in these journals that are all available in my ResearchGate. Tonight, I'm going to keep this a little bit on the fun side and certainly on the tractable side to the best I can, because a lot of the physics and math involved will tear your head off, mine included. So I'm not going to do that to you. It's a Monday night, so I'll give you the fun version of it. And really what this has been a really remarkable dream team that kind of assembled itself, and that's a long backstory. And it brought together biologists, which was essentially me, physicists and engineers, mostly through the lens of Georgia Tech, but also some other universities as well. And I got to tell you, this experience has been remarkable. It's really, really fun and enriching to work on projects with people that are very, very far outside of your own field. So, to you people, so folks out there that are educators at any level, you've heard the phrase, there's no such thing as a dumb question. Well, all the educators in the room and go, well, yeah, there kind of is. And all of us have had doozies launched on us sometimes. And you're like, okay, I got to turn this into a teaching moment, right? But let me tell you, a so-called dumb question from an incredibly smart person outside of your field will make you rethink what you've assumed your whole life. And you realize, like, someone will say, an engineer, for example, will look and go, why does the snake do that? And just out of default, I'll say, well, they always do that. And I stop and go, I didn't answer that person's question. Like, wait a minute. I've known that my whole life, and I've never thought about it, which is a really, really synthetic way to go around research. So I should also say at this point, is this working? You guys can hear me? Okay. If you're a physicist or an engineer, I'm going to make a little bit fun of your colleagues, okay? So sorry if I offend you. It's all in good fun. I'm also going to make fun of myself. Everyone gets made fun of a little bit, okay? So how this project started is the field of what some people call biomimicry or bio-inspired design. And so engineers love this stuff. They look to nature, they see an animal or plant doing something amazing and go, wow, we can co-opt that into some form of a device, right? That's what engineers do. They build devices. So an example here, we have this kingfisher slicing through the air very efficiently and very quietly. And that was co-opted into a new nose cone on the bullet train to make it faster and quieter. Classic example of bio-inspired design or biomimicry. And this is I'm going to call this a one-way circuit where nature comes up with this solution to a physical problem in the world, solves it through natural selection. The engineers figure it out and co-opt it. So nature informs the engineers. And that's how this started. So another way to look at it is basically using a bunny rabbit to make a better wrench, which is a ridiculous example, and I made it up. But to get the idea, it's a single directional line of research, and a lot of it goes through the lens of physics, of figuring out what are the physics of what that kingfisher, for example, is doing. What we stumbled on partway through this project is a different take on this. We started to realize that these devices that we were building could help us ask questions about nature that we couldn't have done otherwise. This was not the original intent. We stumbled on this, and what started out as a one-directional build a sidewinding robot with the engineers turned into using the robot to understand sidewinders better. And that, to be honest, is what made this study way more exceptional than it was ever intended to be originally. Okay, so we have the biology side of the dream team. This was myself and my students, studying mainly morphology, behavior, and phylogeny. And then we have the engineers bringing robotics, material science, and biomechanics to the table. And this was all translated between biology and engineers through the lens of physics. And specifically, we had a physicist, Dan Goldman at Georgia Tech, who studies the physics of sand. Okay. I giggled a little bit at first when I heard this. It's like, I grew up in San Diego, California. It's like, dude, I've been to the beach. I've been to Anza Borrego. Sand, I get it. Like, no, first thing you got to know, you can't call it sand. It has to be granular media. Okay. Hold on to that. Granular media. If I say sand, throw something at me. Sand, I quickly learned from hanging out with these folks, is way more complicated and actually more interesting than I ever gave it credit for, right? Depending on its state, it has the properties of a fluid or a solid. Right? Think about it. It's obviously a solid. I can push on it, right? But then I can pour it between two cups. Wait a minute. This substance, this granular media, is changing states depending on what's going on in its context. And that's exactly what this poor chump is experiencing right here. We all know how difficult this is, right? And the reason is this guy is wasting all of his energy of changing sand through a fluid form into a form that's solid enough that he can actually push off of it, right? So he's taking a fluid form like water and compressing it to the point that it acts like a solid. And all the energy it takes to do that is what is exhausting, right? That's why walking up sand dunes is so difficult. And if you add water to the sand, it changes its characteristics. And this is exactly why it's easier to run. Who runs on, people say, I've been running on the beach. Who runs on the dry sand on the beach? No, you run where it's wet by the water, right? Because its properties are different. So granular media has the characteristics of both a solid and a liquid, which makes it fascinating. It also makes it incredibly deal with as an animal trying to locomote across the surface of it. So this started with the Choset lab at Carnegie Mellon University, who for years, completely uninvolved with me or Sidewinders or anything else, had been pursuing snake-based robots for a variety of reasons. And they're really good at it. And Google SnakeBot, and you will see their robots doing astounding things. So SnakeBot was happening, and SnakeBot was doing great. And SnakeBot was engineered for a number of things like investigating tunnels, sewer, and pipes, sewer channels, things like that, but also for search and rescue and exploration missions, because as this group knows more than anybody, right? Snakes can get into and out of anything, right? Everyone's nodding their head. This is a group of herpers, right? Think, for example, a collapsed building, earthquake. Right? It's a collapsed building. It's dangerous. And the dogs can't get in there. The people can't get in there. It's just stacks of concrete on top of each other. But of course, a snake can get in there. So a snake-based robot, they can send it in there without harming anybody, look around with a little camera and figure out if someone's in there. If there's not, stop wasting your time and go look for people somewhere else. Okay, so that's what SnakeBot was designed to do and was very effective at until SnakeBot got deployed to Egypt. It turns out it's incredibly, this is a tunnel, a tunnel, yeah, exactly, underneath one of the pyramids. And archaeologists always want to know what's down these tunnels. And when they're filled with sand like this, you can't get anyone down there. And it's incredibly difficult and expensive to dig all the sand out of this thing, only to realize there's nothing interesting down there. So they called SnakeBot. SnakeBot, go down there and come back out with your video camera and tell us if there's anything interesting down there. SnakeBot failed instantly. SnakeBot could not deal with the sand. SnakeBot got stuck instantly. They came back and they said, we have a problem with SnakeBot and sand. And so they called the granular media expert at Georgia Tech and said, we need to know a lot more about sand to get our robot optimized to work on sand. And he said, well, I know a guy that knows a lot about snakes. Maybe we ought to bring him onto the team. That's when I got the call. Another thing that SnakeBot is eventually intended to do is to survey places like Mars, right? Why in the world do we keep sending four-wheeled or even tank-treaded exploration devices to Mars only to have them get stuck in the sand, right? Sidewinders, as you guys know better than anyone, never get stuck in the sand. Dune Buggy, how many people, figuratively raise your hand, have gotten your truck stuck in the sand? All of us, right? So we decided to use for our study site the closest thing to Mars we could find, which is Yuma, Arizona. That's our study site down there. That's where our Sidewinders came from. And as you know perfectly well, this is what they do very quickly. And one thing I want to point out is this thing's going to do a very abrupt change in direction as I get closer. This is out in Yuma. There it went, right? You see that abrupt turnabout? We're going to talk about that towards the end of the talk. So we got Sidewinders, and we brought it back to what I called the world's most expensive sandbox that we built at Zoo Atlanta for tens of thousands of dollars. And that's just for the sandbox, because among other things, it has this gigantic air pump that can blow mega newtons of sand, of air up underneath the sand and put it into that fluid form that I was talking about. So we can do that with this. It's kind of like an overbuilt air hockey table, but more expensive. So add another $45,000 to this are these 3 cameras that are about $15,000 each that we set up so we can get 3D motion capture videos of the Sidewinders doing their thing at this resolution. Over the entire body of the Sidewinder, we can tell where every iota of that Sidewinder is in 3-dimensional space at 0.2 millimeters resolution. That's what costs $45,000. Rule number 1, don't touch the camera. Do not bump the camera. Definitely do not drop the camera. I realized early on, I'm not even going to touch the camera. So Joe, will you hold this for a second? Nope. Because what we were doing essentially is straight out of Hollywood, right? You know what they're going to do with this actress. They put the landmarks on her body, right? And then they film her with these 3D camera, and then they superimpose Godzilla or some monster or some super Marvel character or something over the top of it so that they get, that's why those Marvel characters that are obviously animated move so realistically, because they're based on an animal or a person or something that was actually moving it. They captured that and animated over the top of it. So we put the morphological landmarks down the length of the Sidewinder. That was one of my jobs, putting little, in this case, that is reflective tape. Sometimes we used nail polish, right? So that was my job to put little dips of nail polish on the head of a Sidewinder. Not recommended, by the way. And then we put them in the world's most expensive sandbox and let them do their thing and filmed it. Got the Sidewinders in Yuma, and we decided we wanted to use their native sand. So this was one of the more, I've had a lot of unusual experiences doing field work. This was near the top. 3 badly overheated dudes walk into the UPS store with 12 or 15 action packers filled with sand and mailed them to ourselves in Atlanta, Georgia, right? The poor kid behind the counter was visibly agitated and did not trust what we were doing. It was these things, sir, what's the contents of the boxes? I'm like, sand. He's like, sand? And I opened it like, yeah, sand. He goes, what are you going to do with this sand? I said, don't worry about it, but we're mailing it to Atlanta, Georgia. He goes, you know how much that's going to cost? I'm like, don't worry, NASA's paying for it. But I said, but do not overnight it. Do not overnight a half ton of sand to Atlanta, Georgia, right? And it cost an exceptional amount of money to do that. And eventually got there. And of course, I forgot to tell the loading dock at the zoo that this stuff was coming in. So then we had a whole nother freak out at the zoo when all these things showed up and they were too heavy to lift, right? So I'm convinced that there are 2 people telling this story to this day. The poor kid behind the counter at the UPS store in Yuma and me. So here's sand being fluidized. And I mainly show this because it's so incredibly cool. This is better than a lava light, in my opinion. And if there was anyone around we were doing this, I'm like, come here, you got to see this, right? If you stick your hand in that, it's in a fluid state. It absolutely feels like you stuck your hand in water. And then when you pull your hand out, your hand is dry. It's a bizarre experience. The real reason we do this, though, is that we want every Sidewinder to run on a fresh field, right? And this certifies that all the sand is across the entire arena is at exactly the same density and that it's completely flat. Okay, we don't want the other Sidewinders tracks in there to get in the way unless that's a study, and we did that project. And it also verifies that it's flat because when you optimize those 3 cameras, it has to know where the level surface is. If that surface is not level, you're going to mess up your data. So this is more than just a cool party trick. It was crucial for collecting the data. So here's a Sidewinder in slow motion doing their thing. And so I don't often get to give this talk to a room full of people who probably have seen Sidewinders. So that I don't have to explain it, except that I will say that I defy any of you to tell me exactly what and how that snake is doing it. We've all seen it 1,000 times, but if I put one of you in spot and say, what's it actually doing, right? I don't think you can do it. Because to my mind, I'm going to be brave and use a pop culture reference that might fall flat on me, but it's kind of like Michael Jackson's moonwalk. It's like you watch Michael Jackson do that, and his feet looks like he's going that way, but he's clearly actually going that way. Okay, that's how disorienting this is, and it also gives you one of the few animals in the world where the head doesn't get there first. Okay. And if you've ever chased Sidewinders, you realize it's not as easy as you'd think, because you think your instinct is to follow the head, except the head is not going that way. The head's going this way. It's really disorienting, just like humbling yourself chasing crabs at the beach, right? How many of you can actually catch those things? Wrong, because your mind is predicting where they're going to go, and you're absolutely wrong about where it's going to go. So time to get the Sidewinders. I took the sand nerds, granular media nerds, excuse me, out to the desert. Our first attempt was in Antelope Valley in California, because I'm from California and I know they're common there. We just had bad luck and didn't find any. So I shifted over to Yuma, Arizona, and we got everything we needed. So if this is how we grew up, most of us in this room, I'm convinced this is how the sand nerds grew up. Okay, so there's sand nerd field work. There's herper field work. These are fundamentally different cultures, people, okay? And the conversations between them sometimes were frustrating, sometimes were really illuminative, and sometimes they were just hilarious. The miscommunication, just talking in circles, just going, we are not even speaking the same language. First thing out of the car, 4 seconds into the first trip, the physicist sand nerd found the wrong crotalus. Like, oops, nope. Step away. Don't touch that one. That's not the one we're looking for. That's a Mojave rattlesnake in Antelope Valley. One night when we were not finding sand nerds, Sidewinders, Dan Goldman was with us, and I said, hey, you're into sand, check this thing out. This is called a shovel nose snake. And I don't know. Oh, darn, I don't think my video is going to work. Oh, here we go. And he said, okay, what's the big deal? What's it do? So I took it to the side of the road and I put it on the sand, and it did this. And he said, whoa, do that again. And he reached through the sand. He said, they're not venomous, right? I said, yeah, don't worry about it. Don't worry about it. And he reached into the sand right here where he thought it was, and it wasn't there. He said, where is it? I said, I don't know. I said, they don't just go under the sand. Lots of lizards do that. Fringe-toed lizards do that. Horned lizards do that. I said, they go under the sand and they don't stop moving. He goes, you mean they swim through the sand? I said, that's how we describe it. He said, well, swimming requires a fluid state, and sometimes sand is in a fluid state. And he just lit up. And that became a whole nother series of papers that I'm not going to talk about today. So the basics of Sidewinder locomotion had actually been described, and these are the big names in the field. And what I have to point out to these folks, these are in chronological order. By the time we got about here, they were using film cameras and slowing them down a little bit. The people who get the real credit here are Mosauer and Coles and Pope, who, after I just told you, I challenged all of you to describe what these Sidewinders are doing, and I said it can't be done. To be honest, they kind of did it. I'm going to put these folks in categories of exceptional observationists, because they got the basics down with none of the fancy equipment that we have. What I wish I could do is bring all these people back and give them the equipment we had, right? Because they did not have the technology we had. They got the basics down, but we were able to take it leagues and leagues further because of the technology we had available to us. But the basics here in Sidewinders is there's 2 points of contact and then these regions of lift, right? So there's up and down in alternating sequence. But just from knowing that, it's still not obvious about how that translates into that oblique movement, that fluid movement that they're doing. And so hold on to that 2 points of contact, because I'll mention that in a little bit. So after tons and tons and tons of work, what we figured out is we figured out kind of what they're doing. So you guys all know what lateral undulation or the horizontal wave of a typical, say, coach whip going away from you, right? And you also know about sea snakes, sea monsters that do this and all the drawings that we see. And you all know that snakes don't do that, right? It turns out sidewinders are doing this in a very, very, very subtle way. And they're also doing this. And they're doing them both at the same time, one step out of phase. So when you look from the side, you can see the vertical wave. The gray parts are the parts that are in contact with the ground, the 2 points of contact, right? When you look from the side, you see this vertical wave, which is a very subtle version of this. When you look from the top, you see the familiar horizontal wave that we have. And again, the gray parts are the parts that are in contact. So they have, if lateral undulation runs a series of undulations down the body of the snake, they're doing that and then alternating different sequences and interspersing these vertical waves. They're doing both in the same time, like up, down, sideways, down, up, down, sideways, down the length of their body in this very, very fluid thing that produces that really mesmerizing locomotion that they're capable of. So now pick a dot on the snake. This is nail polish. And just watch for a second. Follow it and decide, is your dot up, down? Is it moving sideways? What's your dot doing? Okay, mine is just leaving the ground right now. And now moving sideways. Now it's up. You get the point? Even slowed down, it's still not intuitive what these things are doing. So kudos to Mosauer and Coles for being able to do what honestly I can't do. And then enter the technology to tell you what I already told you we figured out about these things. So here's SnakeBot trying to sidewind here. The important part here, this is on flat ground and it's on a hard floor. And it's clunky, but I will tell you, it is actually sidewinding. So now pick a section of the robot and do the same thing. Is it up, down? Is it moving sideways? What's it doing? So the engineers were insanely proud of themselves when we got to this. They flew down from Pennsylvania, said, we got SnakeBot sidewinding. And we all looked at it and said, yeah, man, good job. SnakeBot is actually sidewinding. And then I said, it's kind of slow, but it is sidewinding. And they shot back like, speed is merely a function of battery power and is irrelevant. I was like, whoa. First rule, do not criticize the robot. Engineers get really, really, really possessive about their robots. So I got my hand slapped by the engineers on that one. But I had to admit that they nailed it. This thing is sidewinding. This is after everything I've talked about now has taken about 3 years after we got the sidewinders. So it makes for a fast PowerPoint, but this was not fast work. Okay, so SnakeBot is sidewinding. Hooray. And it's sidewinding on a flat, hard floor, just like this one here. And you're watching it. Then we put SnakeBot on a slope. That's only a 10-degree slope. Oh, I should back up. Let me back up here. SnakeBot is sidewinding on a zero incline hard floor. And what I don't have a video of, SnakeBot also sidewind just fine on a zero incline sand. Okay, so sand stopped being a problem because it was actually sidewinding. So sidewinding does make it possible for a snake shape to move on sand. Okay. Then we put it on a 10-degree incline, and you see Snakebot is completely failing here. Snakebot is now having the same problem that dude on the sand dune had at the beginning of the video. There's a Sidewinder on a 28-degree incline having no problem whatsoever. Although it is being a little bit efficient. You see these little berms it's leaving behind it? That's wasted energy. Okay, so this is not particularly easy, but the Sidewinder isn't failing. And we realize, okay, sidewinding on flat sand and sidewinding on a sand at even a 10-degree slope are different challenges. It's like, okay, that's interesting. So clearly, we now know the Sidewinder is doing something different on a slope than it's doing on flat sand. And we learned that from the robot. Remember how I said the robot started telling us things about Sidewinders? Something we did not think to look for. We did not expect this. And then the granular media expert instantly went into sand on slopes has different properties. It's like, oh, okay. Thank you, physics team, for telling us that, right? The obvious conclusion is the Sidewinder is doing something different and we don't know what it is. So that became the second chapter of this. In other words, this failure became incredibly enlightening. So the snakes are changing some aspect of that combination of vertical and horizontal waves to accommodate these slopes, and we don't know what they're doing. A whole lot of work later, we figured out what the difference is. And to be honest, we could not have done this without the camera. Right. So Coles and Mosauer could not have done this because it's incredibly subtle. It turns out what they're changing is the length of the part that's in contact with the sand. So these are to scale. So this Sidewinder on what slope is this? Level sand. That gray bar shows how long the section of the snake that's in contact with that with the sand is. On a 20-degree slope, you realize it's that much longer. That's what they're changing. They're changing the length of that point of contact, and that makes the difference. And then we realize if you put it on a 22-degree slope, it gets a little bit longer. A 25-degree slope, it gets a little bit longer. It's like, okay, these Sidewinders are assessing this slope and correcting in real time. Yeah, question.
Does the portion that's in contact ever crest the peak, or does the side elongate? So the gray area.
Yep.
Does it ever go beyond the peak of the wave?
No. Good question. It does not. So this is interesting because it means the Sidewinders are assessing their local condition in real time. And we're not there with Snakebot yet, but we now know if we know the slope of the sand, the engineers figured out exactly what you need to program Snakebot to do to accomplish that slope. Okay. Sidewinders don't, the robot doesn't have sensors in it, so they can't do that. But if the engineers know the slope, they just tweak the program and then make it go perfectly. Whoops, help me out. Thank you. So, as I've already mentioned, as we learned, and maybe some of this was personalities of the people involved, but the biologists and the engineers really couldn't talk to each other. I already told you I got my hand slapped for criticizing the robot. But thank goodness for physicists. Physicists can understand what the engineers are talking about. And our particular physicist knew a lot about animals, right? And so the physicist really made this work. That was the translator. Example one time. The engineers came down to Atlanta with a new version of the robot, and I'm watching it, and we're thinking about this and talking about that and this sort of thing. And I noticed that they put two little headlamps, little LED headlamps that were shining on the head of the robot. And I thought to myself, oh, that makes sense. It's a search and rescue robot. You need some lights because there's going to be a little camera in there. And so I said something to that effect. I went, oh, I see the headlamps. They said, aren't those cool? I said, yeah, those are cool. And I said, are you going to put a little camera in there? And they go, maybe. I thought, okay, well, what are the headlamps for? And are you guys ready for the answer? Because there was room for them. Well, what do I do with that? I was speechless. I had no idea what to do with that information. I suddenly realized, like, wow, We are not even remotely thinking on the same plane. And that's going to come back to haunt me in my direction a little bit later, where I was talking about something. They looked at me as like, are you insane? What are you talking about? So it went both ways. Thank goodness for the physicists. Oh, here you can see Snakebot has got his rubber suit on so that the sand didn't mess up the gears so much. So they just put a rubber sleeve over the thing. So truths I learned about working with robots. You can make them do anything very precisely. Well, you can't, I can't. The engineers can do that, right? They don't bite, escape, or need food, and they're certainly not venomous. That's a plus. Biologists don't really understand them, and I honestly found them to be kind of creepy. And thank goodness we have engineers to change the batteries, because I didn't touch the cameras, and I'm not touching Snakebot. Here's about working with snakes. As you guys know well, you can't make them do anything. You can't even train them. And this is a biological reality. To get serious for a second, when you watch animal behavior and you see an animal not doing something, you cannot distinguish between the alternatives of it can't do something or it simply is choosing not to do something. That's a conundrum. And that's a hard one to get around. And they absolutely can bite, escape, and need food. And sidewinders, of course, are venomous. And I can't tell you how many times I sat there doing these hundreds of hours of trials thinking to myself, it's like, venom has absolutely nothing to do with what we're trying to accomplish here. This project would be so much easier if we didn't have to be safe, right? No engineers were harmed in the making of this series of publications, okay? Fortunately, I think the zoo and Georgia Tech would have shut this down if someone had been bitten in the process of it, but it never happened. So I'm trained in comparative biology or evolutionary biology, which in a capsule means you can't really understand something in singularity. You get a much bigger perspective by comparing it to the other things around it. And the most efficient way to do that is in the context of a phylogeny or a tree of life, if you will. So here's the tree of life for rattlesnakes. There's our sidewinder right there. And we know it sidewinds. And pretty certain these other ones don't sidewind, but I have to tell you, I've seen things, especially Crotalus scutulatus, in very weird kind of panic situations, do something I'm going to call very floppy sidewinding. I've seen some vestiges in it in at least Crotalus scutulatus and some other snakes that aren't relevant to what we're talking about now. And so I posed to the engineers, I said, okay, we got the sidewinder thing figured out. Let's branch out and see if we can find some of the fundamentals of this behavior, of these behaviors, and some of these other rattlesnakes, trying to get an idea of how this evolved in this single. I mean, how many species are on there? How come only one of them does this? Where did this come from, right? These are the sorts of questions an evolutionary biologist would ask. And so I was explaining this to the engineers, saying, hey, okay, we're done with sidewinders for the moment. Let's do some other species and get these comparisons. And they looked at me and said, well, do they sidewind? I said, no. And they said, well, why would we possibly want to look at that? And I made that same explanation over, and it was like me in the headlights. They just looked at me going, what? What? And then one day, the computer was down, and we're all sitting around doing absolutely nothing while the engineer was fixing the computer. And I thought, I'm going to do this. I went up to the herpetology department of the zoo and I got a prairie rattlesnake, and I brought it down and I put it in the sandbox, and it proceeded to not sidewind, right? But the engineers looked at it and they go, it's having the same problem our prototype had. Bing, the light went off. All of a sudden, the engineers were interested in some other things. I went, I did it. I got them on board. So that started a whole new chapter in this of watching other snakes fail on sand. Look at this. And that's on 0 degree incline. The snake is completely failing like you watched Snakebot fail in that earlier slide. Okay, that's really interesting. I have to admit, this is on loop. This was really kind of pathetic and hard to watch. We did not let the snake do this very long. Okay, this is on loop. Okay, I'm glad I got a film of it because we didn't do it again. But I realized I'd never seen a snake fail. I've seen them miss a mouse or something like that. That's just everyday kind of stuff. But I'd never seen a snake completely fail at something before. This was kind of eye-opening to me. So we branched out. So here we have a different species of Cistrus. This is a Massasauga. So here it is on level sand. It's getting somewhere, but very inefficiently, which is another way of saying very energetically expensively, and cannot sustain this for a very bit. A 10-degree incline, that's snakebot failing all over again, isn't it? It's like, okay, okay, we're now starting to understand failure in snakes and realizing when we know why they're failing. By filming these with the same way, we realize exactly the components they were missing. And the components they were missing is the vertical wave. They weren't doing it, and you can't sidewind without that combination of horizontal and vertical wave. These snakes were doing zero vertical lift, and it turns out it doesn't work. So we already talked about this. You see the length of the black bars, right? So in these actual pictures to scale, you can see that's the amount of contact on that sidewinder on 0 degrees. Here it is on 20 degrees. So here's snakebot efficiently going up a 10-degree slope, just like you saw it fail a few minutes ago. Now it's got his rubber skin on. I'm trying to decide if the headlights are on. I'm not sure if they are or not. Okay. So snakebot is accomplishing this because we have A, gotten it to sidewind properly, and B, we've programmed in how much length you need for 10 degrees because we knew it. If it was 11 degrees, it would be different. And then we started to do these what if experiments, right? Like, well, what if? Why do sidewinders have 2 points of contact? Why not 3? And none of the modelers, none of the physicists or engineers could explain to ourselves why 3 points of contact wouldn't work. So we thought, wait a minute, we can use the snake to help us understand why they have 2 points of contact and why those particular lengths and all the parameters of everything involved are so fine-tuned. Because if you mess with them just a little bit, it starts to fail. This one has too much contact for the slope that it's at, and it's digging its grave, just like that pygmy rattlesnake was doing. This one, we put too much lift, and it's pitching and falling all over itself. This system is incredibly fine-tuned, and the sidewinders know how to read their local environment and nail it. Because we all know there's no sand dune in the world that's a steady 20 degrees or 22 degrees up its entire length, right? Sand dunes do this. So we haven't gotten that part with the robot yet. But now understanding failure became really, really interesting, and it helped us understand how finely tuned these sidewinders actually are. So another way to look at this, right, when I teach my classes, the first thing I tell my students is, yes, do go and watch all those awesome natural history videos. David, BBC, Nature, National Geographic, and all these, because the footage they get is amazing. I always tell them, turn the volume off. Right? Because the script that goes over these incredible footage is oftentimes okay for BBC and National Geographic, do awful on like some other channels that I won't disparage. And I tell my students, you need to stay away from this term perfectly adapted because it's a time bomb that's going to blow up on you, right? So a phrase you might hear, the tiger shark is the perfectly adapted marine predator. It's like, whoa, wait a minute. Have you really looked at this? Have you established that there's no possible better way to be a marine predator? No, you have not. You cannot say that the tiger shark is perfectly adapted because you don't know and you haven't done what we've been doing with this particular singular system. But we realize the engineers use the phrase optimized all the time. We realized the engineers could say something is perfectly optimized. And we realized SnakeBot was now perfectly optimized with the right program for all these different sand conditions. And I thought, perfectly optimized sounds a lot like perfectly adapted. It's like, this is interesting. This is really, really interesting. So this is a little hard to follow, but basically what I'm going to show you is the white part here on these different slopes. And here's the percent of the body of the snake in contact, how long those contact sections are, which we know changes as the slope changes. And we now know that within this effective zone, which is what the sidewinders are doing, they nail it. And by modeling the robot to step outside of what the sidewinders are actually doing, we saw all those failures I just showed you. So this is a very narrow window that gets narrow as the slope gets steeper. And we know that you step out of that just a teeny bit and it fails. And I realized for the first time, only time in my career, I am dangerously close to being able to get away with saying something is perfectly adapted. I still can't bring myself to actually say that outside of this context, but we're really close because we perfectly optimized SnakeBot. And we did it based on what the Sidewinder is doing, and we understand all the parameters of failure. And I realized, you know what, folks? Sidewinders, I think, are perfectly adapted for what they're doing. Right? It's like, ooh, but I will not say that on National Geographic or anything. I'll never do that outside the context of this. I just can't. I was just trained too inherently not to do that. So we can program alternative locomotor patterns that we never observed in the Sidewinder. Make 3 points of contact, doesn't work. Change the amount of lift, change the amount of length. It all fails. It all fails. So we fully understand the causes of poor performance and failure in non-sidewinders, right? All those other rattlesnakes, we now know exactly why they failed. There's a, actually, I'll skip that slide. That's a little jargony. But this is the point where I finally learned to love the robot, right? Making the robot was never my passion, but I realized in making that robot, we were going to learn a lot about sidewinders. That was my passion in this project. Have fun with the robot. Glad you got what you wanted. I got what I wanted. I learned a lot about sidewinders. But when I realized the robot could help me understand more about sidewinders, I went, you know what? The robot's kind of cool. Maybe, okay. I like the robot now. This came pretty late in the process. So here is sped up. This is a different aspect of it, looking at turning, right? So we'll go around. Now it's going to turn in place. And it's going to exit the little maze. Okay. So it's being, okay. So here it is. It's going to do what we call a differential turn to go around that slope. Then it's going to do a reversal when it gets down at the bottom. That's what you saw it do on the road in Yuma. That's a reversal. And there's a turn in place and it goes out. So turning in Sidewinders wound up being really interesting because it has to do some weird machinations to pull off this differential turn. And then this reversal turn is a completely different set of behaviors. And then this turn in place, again, this is where the robot became more interesting. That turn in place, the engineers figured that out. They figured out how to manipulate the basic parameters of Sidewinder behavior and accomplish this turn in place that we have never seen the Sidewinders do. We now know they've got everything they need to do it, but we've never seen them do it, which comes right back to what I was talking about before. Can they not do it? Which means they don't have what the engineers would say the software, or what I would say is the neural circuitry or the behavior patterns to do this? Or are they stubborn and after hundreds and hundreds and hundreds of hours of watching them, we've just simply never seen it yet? I don't have the answer to that question, but kudos to the engineers for figuring out that Sidewinders have everything they need to do it. They just apparently can't, or at some point, I can let Bob in. There we go. You help me out. Thank you. So what began as a one-way bio-inspired design study turned into a full circle of reciprocal illuminations. We optimized the world's first sidewinding robot based on snakes. This bio-inspired design taught us a lot about the evolution of Sidewinder behavior because we now could use the robot to do experiments, these what if we do it this way, what if we do it this way, that you can't look at a Sidewinder and tell it, say, hey, try it this time with 3 points of contact. You know that doesn't work. And pulling all this together using robots to ask questions about biological systems, we created a really cool new paradigm for studying biomechanics, which is what we started doing with the shovel-nosed snakes that are truly swimming under the sand. And that lab has moved on to centipedes. I was invited, but I don't know anything about centipedes, so I decided I'm not involved in that part of the project. So what began as a one-way line of inquiry became a reciprocally illuminating line of inquiry, which was really, really a fun thing to be involved with. Closure on a vaguely related topic, but it's so cool because I'm trained in morphology. I can't not mention it. I was looking in the literature one day and found out that some engineers actually figured out that if you zoom in close enough on the ventral scales, the belly scales of snakes, they've got these nanostructure rear-facing spikes on them that you can't feel with your finger, you can't see with your eyes, you got to zoom in on it. And I looked at how those are working. I went, wow, that's a Mexican lance-headed rattlesnake that doesn't sidewind. And I thought, look into that. I go, everything I know about sidewinding says that should impede sidewinding. And I thought, I don't think sidewinders are going to look like this. No one had ever looked at sidewinders. And sure enough, when we got to sidewinders, they don't. You can see the vestiges of those rear-facing spikes, but you see they're infinitesimally small. This is SEM level microscopy, and they've got these weird pits. So we're able to model why that won't work. We now know that doesn't work, right? And we're able to model why that does work on sidewinders. But I'll be honest with you, we don't know the function of those pits. We don't know why those are there. And this got cooler when I thought the obvious questions like, well, what about these unrelated African sidewinding vipers, like saw-scaled vipers and these sorts of things? It was like, So we looked at them with the hypothesis. I said, you know what? All the other true vipers look like this. We did that work. This is all in this paper here. And then sure enough, that remarkable convergence between the sidewinding pit viper, sidewinder, and the sidewinding true vipers in Africa, the true sidewinders also look like this. So that convergence extends itself to the nanostructural scale on the bellies of these snakes. There's a whole lot more to this study, but I don't have time to go into that. So this came out of the Georgia Tech Mendelson and Zoo Atlanta Mendelson lab. And I'm going to end with this great quote from Clifford Pope. A study of sidewinding is recommended for anyone who likes to be confused. Yeah, no kidding, Clifford. Dr. Pope, you nailed that one. Thanks. I'd be happy to take questions, but there's a caveat. I don't hear well, and the batteries in my hearing aids died on the way here this afternoon. So please speak up. And my awesome student, Megan Wright, is going to be my loudspeaker for me. And thank you for repeating the questions for me. Sorry about the hearing aids. Yeah, Dale.
I'd like to ask 2 questions.
Yeah.
Did they ever get snake bot to sidewind facing a consistent direction? Sidewinders hold their head in a consistent orientation while their body is doing all those other wonderful things. It looks like the snake bot's
head. No, and I'm not going to say the engineers couldn't do that, but they just didn't pursue it. They're trying to get snakebot to move across the sand, and we never even really talked about it, and they just never tried. I'm sure they could do it. I mean, these engineers I learned can do just about anything if they put their mind to it, but it wasn't necessary for what they wanted snakebot to do, so they just never chased that. But your point's a good one, right? Sidewinders are doing this, right? With the head being perfectly static, just like watching a cheetah go full speed across the plain. The body's doing all this amazing stuff, and the head is stock center. Yep, snakebot they never even tried.
Search and rescue.
Yeah, they got exactly what they wanted. And your second question?
Were you able to also look at the ability to sidewind backwards?
In the reverse turn. The reversal turn is effectively that. Yep. Yeah.
We're looking at velocity on flat surface. Look at bipeds and quadrupeds. They change gait. They go from walk, gallop, trot.
Right.
So do these guys change gait? Flat surface?
Not at all. All they change. That's an excellent question, and when we went into understanding as they change slopes, we're trying to figure out that something they're doing something different, and we thought about something that would look like changing gait in mammals, which is what you're referring to. They don't do that. All they change is that length in contact. We had some baby sidewinders born during this study, and I got really excited. If you ever seen a baby sidewinder, they are really small, and I thought, ooh, does this scale up? And I got all excited, and I got the baby sidewinder down, and we filmed it, and we all went, it's doing exactly the same thing. So there's no scalar difference, and there's to use the word gait in terms of us. Actually, what sidewinders are doing is kind of like a gait, because they are lifting just like I'm lifting my foot and moving it forward. Sidewinders are effectively having a gait. They are taking steps in a sense. So the word gait is not irrelevant to sidewinders. But no, there's no change in any of that we found. The only change is that amount in contact. Oh, before we get too far into this, I should also say that when you collaborate with people very, very, very far outside your field, there are sections of the papers we wrote that I can't read. This is where you have to trust your collaborators, right? Because the sections I wrote, my collaborators can't read. And I've given this talk before, and I've had the experience where there's a physicist in the back. They ask a question like, I can't answer that. I wasn't on that team. So forgive me if someone asks a question, I go, I'm sorry, I can't answer your question. Read the paper and email the other author if you still have the question. Other questions? Yeah, Robert.
Bob Easy.
Oh, one. Hi, Bob Beasy.
I don't know if my microphone or not, but how do you do?
You showed a phylogeny. Is there a phylogenetic pattern at all here? No, Bob, there is not. Great question, and that's what I was kind of hoping to look for. The phylogenetic pattern is sidewinders do this, nothing else does it. As I mentioned, I made allusion to the sloppy, bad sidewinding that you can see. Baby garter snakes do this. You put a baby garter snake on a floor this smooth, they'll thrash around. And some elements of that are vaguely reminiscent of sidewinding, but I didn't see any phylogenetic stepwise pattern leading to the evolution of sidewinding, Bob. Great question. And that's kind of what I was wondering if I would see, and we just absolutely didn't. A question back there.
About the, I don't know if you can hear this with your impairment, but what about the microstructure? Does it show other ventral scales? Does it show any?
That's an excellent question. And we did not do that work because a colleague of mine, Dr. Jessica Tingle, did all that work for her dissertation, and she found 0 skeletal differences. And she figured that out pretty quickly. And she thought, okay, it must be muscular differences. The muscles used in snake locomotion are this really complex, long muscles with these tendons that span multiple vertebrae. And she thought, oh, those must be different. And there must be something to do with the lifting. And she found a very minor difference in one of the muscles that even she decided was probably negligible. So no, there are not any morphological differences, which means it's all behavioral in the neural circuitry of these snakes.
Wow, Joe, I want to thank you. Many, many years ago, you sent Xanthussia vigilus utahensis to Jack. I want to thank you after the decades for doing that.
No. According to Jessica Tingle's work, no, the answer is no, which, to be honest, surprised her and surprised all of us. When she started on that, said, that's great. I'd kind of been thinking about that, but I'd never even started it. And she expressed interest. I'm like, you go with that. You go with that. It became a big part of her dissertation. She's also the woman who did all the work on looking at bad sidewinding across all snakes and characterize that. It's a really, really great body of work. And I'm glad she did it because we were busy doing this. But no, your questions are absolutely not dumb questions. And we all expected there to be differences, and there weren't. Yeah, in the back, Megan, you're going to have to help me on this one.
Hypothetically, if you have a sidewinder that was twice as long, so twice the number of vertebrae, would it use more than 2 points of contact?
So the twice as long part we looked at when we started comparing the patterns between, for example, the newborns, and then of course we had a dozen sidewinders. They're all slightly different lengths, and that's where we found no difference at all. Your hypothetical situation is a really interesting one, though. If we say a sidewinder has, I'm going to say 122 vertebrae, that's in the ballpark, but I kind of made that up. Yeah, what would happen if they had 400 vertebrae? We haven't modeled that. That would be really interesting because it's hard for me to imagine the space between those 2 points of contact. But we now know that if you have 3 points of contact, it doesn't work. And thinking on my feet here, I think maybe sidewinder vertebral number is in the ballpark of all other rattlesnakes. But I'm starting to think there's like, oh, there might be a reason they don't have 400 vertebrae. But the real answer to that question is probably they don't because they're rattlesnakes. But that's a really neat point. I had not thought about the vertebral number. Yeah, Robert, and then back here.
So in 8th grade, I counted vertebrae on different snake species.
Okay.
Rattlesnakes, gopher snake, king snake, and they had different vertebrae numbers.
Mm-hmm.
Their ability to crawl in a straight line from a push point.
Oh, you did this in 8th grade? Wow. Okay. Good for you.
Snakes figured out where on the live snake every 5th vertebrae is, and I marked it on the live snake.
Uh-huh.
And I didn't use sidewinders, but the rattlesnakes had fewer vertebrae for the length of their body.
Yes.
And the more vertebrae you had, the more difficult it was to maintain a straight line.
That's an interesting correlation. We haven't gone down the pathway of vertebral number yet, which is actually kind of what the question in the back was saying. So kudos to that observation. And I really don't have any comment on that, but the sheer variation in vertebral number. If you guys know what a blunt-headed tree snake is from the tropics, Imantodes, they have like 400 vertebrae. Yeah, it's insane. And they can bridge. Yeah. And yeah, so there's huge variation in vertebral number in snakes, and we have very little idea of why or what that allows them to do or not do. Yeah, question. There are, I think, 3 described subspecies of sidewinder. I'll be honest, I don't find those 3 subspecies to be fundamentally different in any real way, except for some color pattern differences. And one thing you'll notice if you're paying attention to this, sidewinder is kind of like speckled rattlesnakes or tiger rattlesnakes. Their color pattern matches where they're from. We had one snake that came from a little bit outside of our study site in Yuma, and it was a different color. It had a different ground color. So we didn't do the root of your question. I'm going to read is to look at geographic variation in sidewinding, and we did not explicitly do that. I don't have any reason to think that it's going to be any different. But I'll also remind everyone, by the way, that and you probably knew this, sidewinders sidewind all the time. Sidewinding works great on every substrate. I don't know why more snakes don't sidewind because it's efficient and fast. I don't know why more snakes don't do it. It's obviously an adaptation for sand, but it works on everything, and they do it all the time. It's rare to see a sidewinder moving like a normal snake. I've seen it, but it's in very special circumstances. An easy example is, they go down rodent burrows in the day because it's too hot, right? You can't sidewind in a burrow, people. Doesn't work, right? They're using regular rattlesnake locomotion, go in and out of the burrow. And when they come out of the burrow, I've watched them, they'll go a little bit, moving just like a Mojave rattlesnake or a diamondback, and then lapse into sidewinding. So they can do it. They just choose not to do it 99.9% of the time. Yeah, the blue shirt. Mm-hmm. No, that has not been done. And it's an interesting idea. And I'm not sure how one would do that except to put, for example, that poor pygmy rattlesnake that was failing so badly and leave it on sand for years and see if it figures it out. Part of me thinks that's a really interesting thought question. and it's a very interesting basic question. It's a really interesting thought question, but I'm also concerned it might be kind of cruel. I don't think I could bring myself to put a snake in a situation where it can't function. So great question, but I can't think of a way to do that I don't think would be cruel.
Example, my chicken poop, it didn't know how to get out till it watched the chicken run away. Then it followed the chicken. You got to give it an example.
Oh, yeah. So my primate behaviorist friends would call that social learning by watching something else do this. That's an intriguing idea. So I'm going to just let this gopher snake live with the sidewinder for a while and see if it can figure it out. That's actually a pretty cool idea. Yeah, black shirt in the back.
The amount of contact on the surface the same for when it was an incline or a decline, so whether they were moving up or down?
Yes. Yep. That's actually a really good question. Yeah, we did descending as well. I just didn't happen to talk about it today. We did a lot of stuff I didn't talk about today. I think I filled an hour with what we did, but so go read the papers and we did a whole lot of other stuff that I didn't have time to get to. Other questions? Yeah, way in the back.
Scoochulatus sidewinds are not very well. Have you considered calling it scooching?
Oh, that's hilarious. No, that had not come across our vernacular, but it is now. Thank you for that one. It must scooch. Yeah, I like that. I like that. That's why it's fun to give seminars, people, right? You get ideas you hadn't thought of and vernacular you might not have thought of. Other questions? Yeah, Dale.
You looked at belly scales, that morphological, and you had some Kyanactus, so obviously you were looking at a very different kind of snake. Seems like there is a consistency in that they're pushing off, like a continuous sort of wave, but as a burn basically in the sand.
Yeah.
Against that. Is there anything about the sidewinder morphology that gives them more traction?
It's that texture that I showed, that microstructure. Yeah. So back to the question about the anatomical differences. Yeah, that's the difference we found. It's in the skin. It's not in the bones and the muscle. And we're starting to look at the skin microstructure on the shovel-nosed snakes, but we're not there yet. Because what's interesting about shovel-nosed snakes is that, and I'm getting ahead of myself. This isn't. We haven't even done the work, much less published it yet. But ventral microstructure in snakes is kind of a no-brainer because that's where all the action takes place in terms of locomotion. But a snake swimming under the sand has got to be, and there are other snakes that do this, it's got to be the only snakes in the world where the dorsal microstructure could make a difference. And that's on our radar, but I can't tell you what the difference is. But we did find on what we did publish on shovel-nosed snakes that I didn't talk about is that one, they don't sidewind on the surface, which is okay, kind of interesting, but they can move on sand on surface just fine. So we haven't figured out exactly what they're doing there. And then we use sand penetrating x-rays to see what they're doing underneath the sand. And we found that the details in the curvature of their body are very regular and specific. And what it sets up the sand underneath the surface to do is that the sand that's in intimate contact all around their body fluidizes, which is why they actually are swimming. Because that the sequence, and the physicists modeled this, the sequence of this very specific way that they curve their body that other snakes don't do. Actually, those of you that do a lot of night driving, you all know from as far out as your head beams go, if you do this a lot, you can tell if it's a shovel-nosed snake at 20 yards because they move differently than everything else. That's the basis of what I'm talking about. a minor perturbation on that weird movement that you've all kind of seen. You do that in the sand, and it converts the sand that's in the, like we're talking 2 sand grains next to their body. It fluidizes those, so they technically are swimming. So I got off topic. That's a whole nother series of papers. Yeah, Robert.
The thing is, we were talking about before people got here was the age of sand dunes in North America is less than 10,000 years old, and that these snakes are couple million years old, and they've had this ability to sidewind, and they just, as you said earlier, they just sort of took off with this type of movement.
Mm-hmm.
And so, I mean, however, even just within a couple of thousand years, it's pretty remarkable. And then that short amount of time that they have taken to this adaptation or this form of movement.
Yeah, Robert's point is dead on. The deserts where these things live are not very old. So I can't tell you how old the lineage that we'll call a sidewinder is, but I could tell you that the context in which this remarkable behavior has evolved is not very old, and that may well be why there are no morphological differences. Going back to that last study, that microstructure on the belly, you notice how I showed that those rear-facing spikes, you can still kind of see them on the sidewinder. In that paper, we also looked at the sidewinding African vipers, and the Sahara Desert is very, very, very much older than the Mojave and the Sonoran deserts. The behaviors are identical, right? But that microstructure, those little vestiges of those rear-facing spikes are gone in the much older African sidewinding true vipers. And the parsimonious way to interpret that is that they've had millions of years to perfect this over the North American sidewinders, and they're further along. So if I had a time machine and move forward X million years, and sidewinders are in North America and the deserts are still here, and this is still happening, those vestiges are going to be gone. That would be the trajectory it looks like it's on, because the African ones are simply look to be further ahead on the same trajectory.
They adapted?
Yeah. Yeah. Oh, you're trying to make me say this, aren't you? Yes. Yeah. All of the belly scale work was done on museum specimens and shed skins. And all of Jessica Tingle's morphological work was all museum specimens. Our work is inherently behavioral, so it was all on live specimens. But museum specimens definitely were involved in, if you look at the bigger picture of what our Sidewinder group is doing, museum specimens figured heavily. Most of what I talked about tonight, except for that slide at the end, was all live animals. It's behavior. It has to be live animals, right? Yeah, next question. Yeah, our granular media expert tells us that that should matter. We didn't quantify that. You can only do so much, right? So we didn't quantify that, but we did try a large variety of different substrates, sandpaper, different types of sand with rocks and all this type of stuff. And everything looks to be exactly the same. And we know that they can sidewind on any surface, but we didn't quantify it nearly to the level that we did here. It's a fully relevant question, and I'd have to defer to my granular media expert to say if it's likely that they would increase or decrease that amount of contact, and that probably is likely. Probably is likely, and the fact that they can do this on any substrate means that whatever differences are involved, they're accounting for it, because they never ever fail. That's a good question.
Having a spatial awareness like a sidewinder.
I think they do have a spatial awareness. I think they absolutely do. And that is what the engineers tell us is like, yeah, we're not there yet with the robots. We're not there yet. That's machine learning, right? And honestly, I think we will be there, but we're not there now. And we never even attempted to go that direction with this series of projects. We were proud enough with what we accomplished.
Well, thank you, Joe.
Thank you all so much. Thank you out in Zoom land too.
If you all need to get submerged, do it now because Maggie has to leave early as soon as possible. But, all right. And she'll give you your shirt and your honorary. Maggie will give you your shirt and your honorary.
Oh, thank you. Okay, I honor Maggie. Right.